Hello class. In this short video lecture, we are going to discuss about the ideal and practical characteristics of operational amplifiers and also the modes of operation. So in the last class, we kind of talked about basics of an operational amplifier and how an operational amplifier will differ from a traditional transistor-based amplifiers and what are its terminals, which are inverting, non-inverting terminal, an output terminal and two power supply connections. And we kind of have a look on IC741, which is LM741, and figuring out the pin layout or pin diagram of that particular IC. So today we will talk about characteristics of ideal and practical op-amps. Because the op-amps has two input terminals, so at some point maybe we need to use both terminals, maybe one terminal at a time. So depending upon what mode the op-amp is operating, so there are various different types, which is differential mode, so meaning that both terminals are going to be used if it is a double-ended configuration. If it is under the differential mode, if only one of the terminal is being used, that's going to be treated as a single-ended. If both terminals are used but with the same input, that's going to be referred as a common mode. So we are going to look all these three different modes and applications of each mode along with the actual characteristics of an op-amp. So now let's look at some of the parameters of an op-amp, which are some of the internal parameters. So as we are aware of, this particular terminal is an inverting terminal and this terminal is a non-inverting terminal. And I'm going to assume the current going into the terminal of an op-amp, which is current going through the non-inverting terminal, is referring to I+. Current going into the non-inverting terminal is treated as an I+, but the current going into the inverting terminal is treated as an I-. And we already aware of that op-amp requires two power sources, which is a positive VCC or a positive power source, or a negative VEE, or it requires a negative power source as well, and the one output terminal. And here when you observe at the input side, I was shown here as an VID, because the operational amplifier is a differential operational amplifier, meaning that the difference between the input voltage levels is going to be amplified. So it's not the inverting terminal signal, it's not the non-inverting terminal. So operational amplifiers are differential op-amps, meaning that it will amplify the difference between the input signals. So that's what is meant by VID. It's called as an voltage input differential. That's what the ID stands for, input differential. And ZI is an input impedance, ZO is an output impedance, and A is the gain of the whole amplifier. And we already know that the output voltage is going to be calculated if you know the gain, and that gain is going to be multiplied by the input differential voltage. So the output of an amplifier is gain times the input, but the input to an op-amp is a differential input. So it is the difference between the voltage at the non-inverting terminal to the voltage at the inverting terminal. So it's always the differential input. Whether you ground one of these terminals, the op-amp will always amplify the differential voltage. So the output voltage is always gain of the amplifier times the input differential. So the gain of the amplifier could be any value depending upon whether op-amp is closed loop or in open loop. So we will talk about the open loop and closed loop feedback systems later on in the design of these amplifiers. So now we will go on to the actual characteristics of an op-amp in terms of an ideal op-amp. So most ideal op-amp should have at least these characteristics. So similarly, this I plus and I minus, as I spoke before, currents into the inverting, non-inverting terminal of an op-amp, and into an inverting terminal of an op-amp. VID stands for input differential voltage. Again, it's an always differential, meaning that the operational amplifier will always amplify the difference between the input terminals. Plus Vs and negative Vs, that represents a source voltage. Op-amp requires two power sources, positive and negative. Usually plus 15 volts and negative 15 volts is being used. Both voltages usually should be equal to each other. If you use a plus 10 volts as in VCC, you should maintain or you should cope up with a negative 10 volts as at the VEE. There is a reason for that too. We will talk about when we get into the usage of the capacitors along with an operational amplifier. So the main reason for that is removing the DC components that may occur because of the voltage variations on these power supplies. So we will get into that concept later on. So ZI, that's an input impedance. So if I'm looking from the input point of view, the impedance or the total resistance is a combination of resistance or the internal capacitance. It's going to be treated as an impedance. So input impedance, for an ideal op-amp, the input impedance should be infinite so that we are not going to load the source. So A is the gain of an amplifier. So ideally the gain of an amplifier is infinite, but practically it's going to be very, very huge. And there are some applications of having an infinite voltage gain or very higher voltage gain, but those applications are limited, which we talk about in open loop applications of an op-amp. And some of the applications are using a comparator, meaning that if you want to compare two voltages, whichever is greater, less than, or equals to. So those are the applications that requires a much higher gain. So output impedance, ZO is the output impedance. Ideally, it could be 0, meaning that if the load requires more current, then the op-amp stage should be able to give that much of current. So whatever the load wants, then the op-amp should be able to give that amount of current or provide that current to the load. So that's why the output impedance should be always or at least close to 0. The output voltage, we talk about output voltage is always gain of the op-amp times the input differential voltage. But right now the gain is referring here as an AOL, that stands for gain of an open loop system. So meaning that there is no feedback. The signal is not feeded back, or signal is not comparing with an input signal. Usually, as I said before, open loop systems are going to be used for a comparator or very high voltage gains, but there are very limited applications using an op-amps. But when again we will get into the open loop configuration. So in the previous figure, there is no loop back. The output signal is not fed back somehow into the input side. So that's why this configuration is treated as an open loop configuration. Whenever you see a feedback, no matter what, whether the output signal is fed back into a non-inverting terminal or whether it is feeding back to an inverting terminal. So those refer to as a closed loop systems. But the open loop systems means there is no loop which is going around output to an input. That's why open loop gain is much higher. And as an amplifier, the op-amp uses only a closed loop configuration. So let's look at some of the key concepts of or key characteristics of an ideal op-amp. So how we want an op-amp to be in the real. So it should have an infinite voltage gain. So meaning that if I give a minimum voltage, the op-amp should be able to amplify without any losses. And we also aware of that no amplifier can amplify greater than its power source. So when we talk in the power amplifiers, we talk about output voltage of any amplifier will not exceed the maximum power source. Let's say, for example, if your DC power source is 15 volts, the output of the amplifier will not exceed 15 volts. It should be the maximum voltage you can get is 15 volts. At the same time, the negative voltage you can get is a negative 15. So that meaning that that particular amplifier has a very high or very huge gain in order to maintain that. So practically, the voltage gain can be limited based upon using a feedback systems. So instead of using an op-amp as an open loop, if you use a closed loop, you can reduce that gain from infinite voltage gain to a very finite voltage gain for a practical purpose, and it has a more advantages than the open loop. So in truth, it's going to be around 200,000. So even at the input side, if you apply a 10 millivolts, then the output is going to be, so you can do your calculations, 10 millivolts is approximately, being this gain is going to be 2000 volts. So even very small signal is going to be amplified to a very huge in an open loop configuration ideally. So infinite impedance, so that we are not going to load the source. So infinite impedance meaning that infinite resistance. So if the resistance is too high, then according to Ohm's law, the current will be approximately equals to 0. So ideally speaking, there is no current entering into the terminals of an op-amp because of very high input impedance. In truth, it's around 10 to the power of 12 ohms. So zero output impedance, so that you can supply as much as current as the load wants. So ideally speaking, the op-amp should have a very less output impedance, which is 0, but practically it's going to be in terms of an order of ohms. So infinitely fast. So nowadays we want all the circuits to be very fast as possible. So if you apply an input signal, so it doesn't matter whether it's your voice signal you want to amplify, you want to get the response at the output side as quickly as possible. So the slew rate of an op-amp, that's a parameter that will talk about how fast an op-amp could be. So once you apply an input signal, how fast you can receive that response. So, or how fast the op-amp will change its output rate. So that's going to be called as a slew rate. We're going to again talk about how to calculate this slew rate based upon the input signal later in the discussion of operational amplifier parameters. So in general, it's going to be around 0.5 volts per microsecond. So in the last class, I talked about if you go through that particular link of the data sheet for LM741, you will observe all these various different characteristics. So what is the input impedance, output impedance, slew rate, and what is the bandwidth of the signal. So the bandwidth is based upon the frequency of operation of an amplifier. So usually it will limit it for our IC741. Usually it's going to be in the order of megahertz range. So ideally speaking, op-amp should have an infinite voltage gain. It should have an infinite input impedance so that you will not load the source. Zero output impedance so that you can give as much as current the load wants. Infinitely fast and infinite bandwidth. But we are aware of that no circuit in the real or practical manner is ideal. So we are trying to get to these characteristics, but every time we are short of the ideal characteristics. So meaning that if you apply a VCC of 15 volts, we are expecting the maximum output voltage is 15 volts. But in the reality, the maximum output voltage you will get is 14 volts or close to 14 volts. You are not going to get 15 volts. So ideally case is a 15 volts output for a 15 volt source, but practically you will get a 14 volts for a 15 volt source. So those are the characteristics of an ideal op-amp. So it's very important to understand these ideal characteristics because we are trying to implement our circuit so that the characteristics of the practical circuit will meet the ideal circuit characteristics or as close as possible. So let's look at how to connect these operational amplifiers because this operational amplifier has two input terminals. So how many input terminals we are going to use? We are going to use whether one input terminal, two input terminals, or both input terminals. So depending upon how or in what mode the operational amplifier is connected. So the next couple of slides are going to concentrate on various modes of operational amplifiers. As you can look, these two circuits right here are connected in the single-ended configuration, and of course it's a differential input. Again, operational amplifiers or differential amplifiers, so it's going to be single-ended differential, double-ended differential, common mode inputs. So let's look at the single-ended. If you observe these two circuits together, there is a one common ideology that you can look here. The input source, if you observe, the input source is both input source are sinusoidal, but for the top circuit the input is applied to the non-inverting terminal of an op-amp, whereas an inverting terminal is grounded. But for the bottom circuit the input is applied to a inverting terminal, but the non-inverting terminal is grounded. So comparing these two circuits, one of the terminal is going to be grounded, whether it is a inverting terminal or whether it is a non-inverting terminal, and the signal is only applied to one of the terminal. That's why it's called as a single-ended configuration. So the signal is only applied to one of the input terminals but not both. One of the terminals should be grounded if the op-amp is in the single-ended configuration. But let's look at some of the facts. If the input is applied to the positive terminal, so in this op-amp, the output will be amplified version. So let's say, for example, I give a 10 volts input, and the gain of this amplifier, so let's treat the gain of this amplifier is 2. So that's the gain of this amplifier. So the expected output voltage is gain times the input, so that's going to be 20 volts. So for a 10 volts input, the op-amp has a gain of 2. I will get a 20 volts. Because the input signal is applied to a non-inverting terminal, the phase relationship between the input and output terminals is 0 degrees. Both are going to be in phase. In addition to this amplification, if I apply the same characteristics, so even if I apply same 10 volts here, and if this amplifier has a gain of 2, then the result is going to be 20 volts. But the signal is applied to a inverting terminal, so I am having some amplification, but the difference between input and output phase shift is 180 degrees always. So if the signal in the single-ended configuration, if the signal is applied to a non-inverting terminal, there is always 0 degrees phase shift. So meaning that if the input signal is at 0 degrees, the output signal is at 0 degrees. If the incoming signal or the input signal is at 180, the output signal is also at 180. There is no phase difference. If the signal is applied to an inverting terminal, there is always 180 degrees out of phase, meaning that if the input signal is 0, the output signal is out of phase by 180 degrees. If the input signal is 180, then the output signal will be out of phase by 360 degrees. So there is always a phase change between input and output signals of 180 degrees if you are using an operational amplifier where the input is connected to an inverting terminal. If the input is connected to a non-inverting terminal, there is no phase shift at all. So these two configurations are referring to as a single-ended configurations because only one of the input is receiving an input. Another input or another terminal of an op-amp is grounded. So let's look at another mode, which is a double-ended differential input. So the term says it's a double-ended, so meaning that two terminals of an op-amp are going to receive the input. In the single-ended, only one of the terminal is going to be receiving an input, but here two terminals are going to receive the input. So when you observe here in the top diagram, there is only one source, but that one source is connected to the both terminals, positive and negative. When you observe the bottom figure, There are two different sources, V1 and V2 are connected. V1 is connected to the non-inverting terminal, V2 is connected to an inverting terminal. So both terminals are going to receive some input other than ground. That's what the double-ended configuration. But let's look at some of the facts of the double-ended. So let's consider an example. Okay, if I apply V1 is 5 volts in this particular double-ended configuration. So what is an expected output voltage? So assuming that, okay, let me assume the gain of this amplifier is 1, right? So if you think of the positive of the voltage source is connected to the positive input and the negative of the source voltage. So meaning that if the V1 is 5 volts, here I'm applying 5 volts and here I'm applying negative 5 volts because the negative terminal of the input is connected. And we always aware of OpAmp will do differential. So it will always consider the input voltage or VID, V input differential is the difference between voltage at the non-inverting terminal minus voltage at the inverting terminal. So in this particular example, the voltage at the non-inverting terminal is 5 volts minus the voltage at the inverting terminal is a negative 5. So which will gives you 10 volts differential input, and with a gain of 1, 10 times 1 is 10 volts. So the output is going to be 10 volts. So if you want to amplify the signal greatly, then the input terminals are going to share the same signal. So even though it's having only one single source of 5 volts, the output is going to be 12 volts with a gain of 1. So now when I look at the second circuit, here I have two input sources. V1 is, so let me assume that V1 is 5 volts, V2 is 5 volts. So the output voltage is an input differential voltage. So which is going to be the subtraction between, again it's the same formula, VID is V plus minus V minus. So the input voltage is 5 minus 5. That input itself is going to be 0 volts. The VID itself is a 0 volts. So no matter what the gain of this amplifier is, the output will be always 0 volts because the input differential is 0. So whatever the gain we considered, so it doesn't matter if the OpAmp has a gain of 1, 0 times 1, that's going to be 0. The OpAmp has a gain of 2, 0 times 2, that's going to be 0. So no matter what, the output will be 0 in this particular configuration. But comparing these two circuits together, both are coming under double-ended configuration. So even though the top circuit has only one single source, it's still going to be connected. It is connected to both terminals of an OpAmp. On the second circuit, I have two sources connected to an individual terminal, two different sources. So the output is going to be the gain times the difference between those two inputs. So if I consider another example, let's consider the V1 is 10 volts. So I have this V1 10 volts and V2 is maybe 6 volts. Let us change the gain of this OpAmp from 1 to 2. So let's look at how to calculate the output voltage of an OpAmp. So output voltage is always gain of an OpAmp multiplied by input differential. So that's the differential voltage. The gain of an OpAmp is given as 2 multiplied by VID is a subtraction between voltage at the non-inverting terminal to the voltage at the inverting terminal. So in this case, it's going to be 10 minus 6. So 2 times 10 minus 6 is 4. So 2 times 4 is, that's 8 volts. So the output voltage is an 8 volts. So what it does is, it will take the difference and it will amplify that difference voltage. So the OpAmps will always be input differential voltage. So let's look at another important mode which is used in the elimination of noise for these operational amplifiers, which we call as a common mode. When you observe, this is the circuit that we use for a common mode configuration. A common mode is nothing but it is a double-ended configuration. It's not a single-ended configuration because none of the terminal is grounded. So common mode meaning that it is a double-ended configuration. But it is a special case of double-ended configuration where both terminals are receiving same input. So let's look at that. So let's say I'm applying 5 volts input. That's the positive side of the supply. This is the negative side of the supply. Negative is grounded. So 5 volts is applying to the negative terminal and the same 5 volts is applying to the positive terminal. So what happened to the VID now? Because of the same voltage is applied to the both terminals, the VID is 0. If the VID is 0, no matter what the gain of an amplifier is, the output voltage will always be 0, ideally speaking. So same voltage source is applied at the both terminals. Again, common mode configuration is same as a differential mode, except the signals at the both terminals are going to be the same. In the double-ended configuration, you can look, there are two different sources. You can apply same voltage or a different voltages, so it doesn't matter. But still both configurations are double-ended configurations. Common mode meaning that the input to the op-amp for the both inverting and non-inverting terminals are common or same. So ideally two inputs are equally amplified. So meaning that, so I have a 5 volts and 5 volts here, the input differential is 0, so the output voltage is going to be 0. So output voltage ideally is 0 because of the differential voltage is 0. But again, no circuit is ideal in nature. Most practically, usually there is some error voltage exists at the output side of an op-amp. Even though if you apply a 0 volts input to an amplifier, we're expecting 0 volts output. But practically, without any signal input, you are going to get some error voltage. Maybe because of the temperature changes, maybe because of the change in terms of a barrier potential of these transistors, which we call as a VBE, which is we assume as a 0.7 volts. Because of that voltage, there is always some current. If there is an voltage, there is a movement of electrons. So if there is a movement, there is a current. So even though there is no input signal internally, there may be possibility that there is a current and there is a very small error voltage. So let's look at later on what is the advantage of having same signal at the input side, because always, no matter what, if you apply same signal, you will either get 0 or an error voltage. So what is the purpose of that one? Think about it, and we will discuss that concept in the next class or in the next video lecture on why we require to have these common signals. So some of the quick summary for the differential circuit: opposite inputs are highly amplified, common inputs are slightly amplified. If the signals are common, if the signals are same, then it's very, very small in terms of a millivolts or microvolts. That's how it is going to be amplified. If the signals are opposite, as you can see in this particular example here, 5 volts and negative 5 volts at the input side are greatly amplified. So those are the various modes or various configurations of an operational amplifier. So we talk about a common mode, differential mode, which is in terms of a double-ended, at the same time single-ended. And we already also talk about the difference between an ideal op-amp versus a more practical op-amps. So that concludes this particular video on operational amplifier modes and difference between ideal versus most practical op-amps.